Hi, my name is Bruce Bouquet, and I'm from the New Jersey Institute of Technology. Welcome to Numerical Methods, how to use computers to solve difficult math problems. In today's episode, we're going to discuss Gaussian quadrature. That is, other methods of numerical integration. Earlier, we discussed midpoint method, trapezoidal rule, and Simpson's rule. The midpoint method just uses the middle of any interval, the y value at the middle of the interval, and multiplies by the width of the interval to get the area of the rectangle. You add those up, and you get an approximation for the integral. The midpoint method has degree of precision 1, meaning that the midpoint method is exact for constants and linear functions, y equal x to the 0 and y equal x to the 1, but not exact for y equals x squared. Therefore, the highest power for which it's exact is 1, and so we say the degree of precision is 1. Similarly, the trapezoidal rule is exact for constants and lines, so it too has degree of precision 1. And Simpson's rule is exact for constants, linear functions, quadratics, and cubics, and so it has degree of precision 3. It is not exact for quartics, for x to the 4th. These methods use equally spaced points. Now we could ask, well, what if we don't restrict ourselves to methods that use equispaced points along the x-axis? Let's try to find methods to integrate polynomials exactly using values, y values of the function at the fewest number of points. That is, let's find maybe if we let the x values vary and give them appropriate weights, then we can get a method that uses fewer points. So let's see, how good can we do with 1 point? Suppose we want to find the area under f of x from -1 to 1, and we're going to use 1 point. So we're going to develop a method that says, in order to approximate that integral, we'll take a certain constant value times the y value at a certain point. Well, if we want to make that exact for y equal 1, we find the exact value of the integral of y equals 1 from -1 to 1. That's equal to 2. And that should equal to omega 1 times the function value at x1. If the function is y equal 1, then the function value at x1 is 1. And so we find that omega 1 must equal 2. If we want to make this method exact for y equal x, we find the true value of the integral from -1 to 1 of x dx, which is equal to 0, and that should equal to omega 1, which we found to be equal to 2, times the x value, because f of x1 is x1. We plug that in, we get 2x1 equals 0, so x1 equals 0, and the method using 1 point on an interval, well, it works out to be the midpoint method, y equals 2 times the y value at x equals 0. So this is exact for y equal 1, and for y equal x, one could check that for y equal x squared, the true value of the integral is 2/3, whereas the function gives us 0. It gives us 2 omega 1 times f of 0. f of 0 for y equal x squared is 0. So we get 2/3 is not equal to 0, and so the degree of precision is equal to 1. This method is exact for y equal 1 and y equal x, but not y equal x squared. Well, how good can we do with 2 points? Now it gets more complicated. What we want to find is a constant times the y value at 1 point plus another constant times the y value at a different point. And we just do the same thing. If y equals 1, what's the exact value of the integral? And we just set up this equation. If f of x is equal to 1, then we just get omega 1 times 1 plus omega 2 times 1 is equal to 2. For y equal x, the true value of the integral is 0, and that should equal omega 1 times, well, if f of x is x, f of x1 is x1, and we plug in and so forth. Then we do it for y equal x squared. And the reason that we're doing it 4 times is because we have 4 constants that we can solve for, so we expect that our method should be good at least up to y equal x cubed. However, these equations are nonlinear, and so there is no guarantee that we'll even have a solution, whether the solution would be unique, etc. And we But we can solve these four equations for omega 1, omega 2, x1, and x2. And when one uses these clever methods to solve it, we find that x1 is 1 over the square root of 3. x2 is symmetric to that, minus 1 over the square root of 3. Omega 1 and omega 2 are equal to 1. And so we have a method that the integral from minus 1 to 1 of f of x dx can be approximated as 1 times the y value at x equal 1 over radical 3 plus the y value at minus 1 over radical 3. One could check that if you use y equal x to the fourth, this method is not exact, and so the degree of precision is equal to 3, but we've only used 2 locations in x. Let's do an example. Our method is that the integral from minus 1 to 1 of f of x dx is approximately f of 1 over the square root of 3 plus f of minus 1 over the square root of 3. Let's consider the case of y equal e to the x. We plug that in. We have 1 times e to the minus 1 over radical 3 plus e to the plus 1 over radical 3. We work that out. We get 2.3427, and the true value is 2.3504. So we're off by less than 0.01, just using 2 points on the interval of length 2 from minus 1 to 1. So finding the nodes and the weights involves the theory of orthogonal polynomials. If we wanted to find a 3-point method, a 4-point method, a 5-point method, etc. If you have n nodes and n weights, that's 2n constants, and therefore one can match up 2n integrals, 1, x to the 1, x squared, etc., up to x to the 2n minus 1, and so that we find that the degree of precision will be 2n minus 1. Well, we only handled the interval from minus 1 to 1. What do we do if we just have an integral from a to b? What do we need to do in order to use this method called Gaussian quadrature for integrals on just a general interval? What we do is we let x equal a plus b plus t times b minus a over 2. And we could check that if t is equal to negative 1, then we'll get b minus b, but a plus a over 2. So if t is minus 1, x is equal to a. If t is equal to 1, similarly the a's go out, get x equal to b. So the integral from a to b of f of x dx will be the integral from minus 1 to 1. F of, well, x is now this quantity. Before we had dx, so we need to change that into dt's. We see that dx is b minus a over 2 times dt. So we plug that in, pull out the b minus a over 2, and we see that the integral from a to b of f of x dx can be written as b minus a over 2 times an integral from minus 1 to 1. And now we have a method for finding integrals from minus 1 to 1, and so we can use what we've just learned for Gaussian quadrature to solve such integrals. Let's do an example. Consider the interval from 0 to 1, and we want to find the integral of square root of x dx, which is 2/3. If you use the points 0, 1/2, and 1, using the trapezoidal rule or Simpson's rule, you get these values. And trapezoidal rule has error about 0.06. Simpson's rule has about half that error, about 0.03. Gaussian quadrature, well, we're going to use b minus a over 2, this integral from minus 1 to 1, f of a plus b plus t, b minus a over 2 dt. Well, we're going to use, with x1 meaning t, because now t goes from minus 1 to 1. If we use the t values 1 over square root of 3 and minus 1 over square root of 3, with the omegas both equaling 1, what do we get? We have b minus a is 1, divided by 2. Omega is 1. Omega 1 is 1. F of a plus b plus t was minus 1 over radical 3. B minus a is 1 minus 0 over 2. Plus, and then we plug it in for the 1 over plus radical 3. And we just use our function as square root of x. F of all this mess is the square root of the mess. And we work it out, and we just get 0.673887. And we see that with Gaussian quadrature, the error is about 0.007. It's about 1/4 of the error of Simpson's rule. So the method tends to be quite good. Now, there's nothing special about integral of just plain f of x dx, turns out that there are certain forms of integrals that are useful that arise from partial differential equations, and we might want exact formulas for the integral with certain weight functions. For example, the integral from -1 to 1 of f of x dx over the square root of 1 minus x squared, or maybe we want the integral from 0 to 1 of square root of x times f of x dx. We can also find quadrature methods in the same manner that are specialized to take advantage of the specific form of these integrals. So for example, in the second case, if we wanted to find a method also with just two x values, that's great on the interval from 0 to 1 for square root of x times f of x dx. We're going to try to force that to be exact for f of x equal 1, f of x equal x, f of x equal x squared, and f of x equal x cubed, because we have 4 constants that we can set. So we just plug in f of x equal 1, f of x equal x, f of x equal x squared, f of x equal x cubed. We find the exact value of that integral, and we write it as omega 1 times f of x1 plus omega 2 times f of x2. If f of x is 1, those just become 1. If f of x is x, we just plug in x1. If f of x is x squared, and so forth, and we work out these exact integrals, and we would solve these 4 nonlinear equations for the 4 unknowns. And we could get a new quadrature method that is particularly good for integrals of square root of x times f of x. So that is another way to go about this. And again, we can transform the interval however we like, in the appropriate manner, as we did before, to solve integrals on different intervals. We have to be careful that we should only use weight functions, square root of x, for instance, in this case, or 1 over square root of 1 minus x squared, in this other case, that are greater than 0 for all x in the interval from a to b. Let's take a moment for culture. During a calculus class one day, there was a lecturer who suddenly checked himself and stared intently at the table in front of him for a while. He looked up, and then he looked back at the desk, and he was all confused. He thought that he had brought 6 piles of paper with him, but he said, no matter how I count, there are only 5 piles on the table. Then he became silent for a little while and told the following story. When I was a young man back in Poland, I met the great mathematician Wacław Sierpiński. He was old already then and rather absent-minded. And once his family was moving from one home to another. His wife didn't trust him very much, and so when they went down to the street with all their belongings, she said to Dr. Sierpiński, now, dear, you stand here and watch our 10 trunks while I go and get a van to move our belongings to our new home. Knowing that he would be no good at all with the moving or finding the taxi, so she left him there, and his eyes were somewhat glazed, and he was humming absently. So after a little while, she returned, presumably having gotten the taxi that would be coming shortly, and she said to her husband, and he said to her, I thought you said that there were 10 trunks, but I only count 9 trunks. And she got all upset. No, dear, there are 10 trunks. I left you with 10 trunks. That's all I left you to do, was to watch our 10 trunks and make sure that none of them get missing, that no one takes any of them. And he responded, no, but no matter how I count them, I only get to 9. Look, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm Bruce Bouquet from the New Jersey Institute of Technology. Thanks for joining us, and may the power of math be with you.